Okay, so this problem, we're going to still try to find internal shear and moment as a function of x in the beam. And I've indicated x is going to go from left to right. So what we've been doing so far is cutting the structure like a method of sections. And then we look at either the left side or the right side and try to decide which one is best for us. If I cut the structure at some distance x, the length of the segment on the right would be how long? Would be the total length minus x. In this case, that would be 18 minus x. So I know that dimension. Let's see what else we need to do. We would need two reactions at A if I went to the left side, right? I would need to know the vertical reaction, which would be AY, or the shear, and possibly a X reaction. On the right-hand side, I would need to know that reaction, which is also a shear. So what I'm going to start doing now is just writing that in terms of shear. If you're on the right-hand side, is positive shear up or down? It is down. That's positive shear at B. This is positive shear at A. Right? Remember, it causes the structure to want to rotate clockwise, and both of those do that. Okay, so really we know the sum of the x will be easy to find, so there's really no clear advantage in terms of the reactions. I've got to find one. Okay, so now I've got, what kind of load do I have on this left side? It's trapezoidal. What kind of load do I have on the right side? It's trapezoidal. So I don't really see a huge difference, except that all my work on this side will be in terms of x. All my work on the right-hand side will be in terms of 18 minus x. So that would just be a little more tedious and cumbersome to carry around. So I think I'm going to go to the left side. In either case, I'm going to need to know what the value of the load is right there. So how can I write this distributed load as a function of x? Well, it's a straight line. And we always know that a straight line, in this case, the straight line describing the load, is AX plus B, right? And what is B? It's the value of the load when x is 0. What is the value of the load when x is 0? 1. So I know that B will be 1. A is then the slope of the line. What's the slope of this line? Rise over run, right? What is the rise? It's a change from 1 to 3, right? So that would be 3 minus 1. That's the change in vertical direction over a run of 18. So that's 2 over 18 or 1 over 9. So I can now write my load as a function of x as equal to x over 9 plus 1. And you can check that, right? When x is 0, what do you get? 1. And that matches. When x is 18, you should get 3. If you put 18 in here, you get 18 minus 9 is 2 plus 1 is 3. So that tells me the value of the load anywhere I want on that line. Yeah?
I don't get it. Why did we do the AX plus B?
That's just the general form of a straight line, right? So this is a straight line. So I'm writing it as a function of W as a function of x. So initially when x is 0, I know my function starts at a value of 1. So that means the constant is equal to 1. Because when x is 0, this term goes away, right? And then by definition, A is the slope of the line. So I just calculated the slope of the line. So from this point to this point, it has a vertical change of 2 over a horizontal change of 18. So that's where I got this. So 2 over 18 is just 1 over 9. Straight line. Okay, so I need to draw a free body diagram of this side because I'm going to go to the left, so I need to probably find the shear at A first. So let's do that. So I'm going to, I think I'm going to redraw this. Since I made so much noise up here, I'm going to redraw the free body diagram of the whole thing to maybe make it a little easier for you to see. So I'll come back and say, here's my positive shear at A. Here's my positive shear at B. The trapezoidal load, now I know the area of under a trapezoid. You probably do too. But I don't remember the formula for the centroid of a trapezoid off the top of my head. So what I usually propose at this point is to take this system and to break it up into two pieces. The first piece being the rectangular piece, and then the second piece being the triangular piece. So just looking at the rectangular piece, what would be the area of that rectangle? Well, it would be base times height. That's 1 times 18, so that's a force of 18 kips. And where's the centroid of a rectangle? Right in the middle. So the first part will be a concentrated equivalent force of 18 kips, and that's located half the distance. I'll just write that as 9. Now what about the area of the triangular piece? So what is the height right here of the triangle? Well, it's 3 minus, right, remember the value here is 1 kip per foot. So the height is just the difference. So it's only a height of 2. So the area of a triangle is 1/2 base times height, and that's also 18 kips. And we also know that the centroid of a triangle is 1/3 from the big end. And what's 1/3 of 18? 6. So I can now fill in, since this is 9, I know this is 3. So I have all the distances I need to locate my forces if I sum moments at either point. So let's now come back and sum the moments about B, right here, and that will allow me to find the shear at A. So summing moments about B, both these applied concentrated equivalent forces create what kind of moment with right-hand rule? Positive. So I'll say 18 kips for the force. The moment arm for the first one is 6 feet. The moment arm for the second one is 9 feet. So there's the moment due to the applied forces. And then I have the moment due to my shear force. That creates what kind of moment about B? Positive or negative? Negative. So I have the shear at A, and that distance is the total length, which is 18. So I should be able to find the shear at A. I think it's going to be positive, and it's going to be equal to 15, I think. So check that for me.
It is.
So I know my shear value at A. Now if you want to be complete, and we will just for this example, I would go ahead and sum forces in the x direction, make sure it's equal to 0. And I just realized I left off my AX force on my free body diagram, but now that it's included, all I would have would be AX. And as we already mentioned, it's 0. So now I have all the information I need to go back and build this free body diagram. So let's do that. And I'll draw it a little bit bigger. Let's see, let me think about this for a second. Just so I'll have some room so you can visualize it. So this would be at some distance x. And I have my shear at A, which I solved for, equal to 15 kips. And then I have a distributed load acting down. And we already know that this is 1 kip per foot. And of course, what's the value at any distance x? Well, we've already solved for it, right? So that's going to be x divided by 9 plus 1, and that would also be in kips per foot. And then at the cut, I'll assume positive shear force and positive bending moment. Those are the two things we're trying to find. And in a similar manner that we did up here, I'm going to divide my trapezoid into a rectangular portion and a triangular portion. And find those two forces, just like we did up here. So looking at the rectangular piece first, what will be the area of this rectangle? This part right here. Well, it's always base times height, right? Base is x. What's the height? 1. So this will be a force acting through the centroid of the rectangle of x. And what's the distance between here? It will be at x over 2. Everybody see that? So I'm going to come down here and make a little accounting of that. So the first force, I'll call it F1, will be x. And the distance from the distance from the cut to that will be x over 2. So I'll even come back here and say, hey, this is F1. Now the second part, maybe I'll do it in a different color so you can see the difference. This green part here, that triangular section creates a different force. I'll call that F2. Now what is the area of a triangle? 1/2 base times height. So F2 is going to be 1/2. The base is x. What's the height of this little triangle right here?
9, 1.
Yeah, because remember this point right here is 1 kip per foot. So the difference would be this minus 1, and x over 9 plus 1 minus 1 is x over 9. So that means my height is x over 9. And if you do that calculation, you get x squared over 18. And the distance from the cut, we're going to sum our moments, to that force is what? It's 1/3 the distance. The distance is x. So I'll say d2 will be x over 3. You can see, so our free body diagram work is getting a little more complicated, a little more detailed. So that's why as we move towards the first exam, I want to remind you that, focus on this and try to get this right, because this is where the bulk of your points are going to be earned. It's still important, obviously, that you can sum moments and forces and solve for the two unknowns and get the right equations. But if you don't get this right, then the rest of it's just not going to go your way. So I think we've accounted for everything. So let's come back now, and I'll put a little line here to kind of separate it visually. And let's sum the moments at the cut and make sure that's in equilibrium. So about the cut surface, using right-hand rule for my sign convention, let's calculate the moments of all the forces and moments. So the unknown moment that I've drawn here is positive. The moment about the cut created by F1 and F2 are both positive. So I'll do the first one. F1 is x and has a moment arm of x over 2. F2 is x squared over 18, and it has a moment arm of x over 3. So I've accounted for these two. And then all I have left is the shear force over here at A, and that's going to create what kind of moment? Positive or negative? Negative. And the force will be 15, and what's the moment arm? X. So So all I have to do is solve for the moment. So when you solve for the moment, it'll be a function of x. I'm going to rewrite the order of the terms, so I put the highest order first. So that would be minus x cubed over 54 minus x squared over 2 plus 15x. And that should have the units of kip feet. So there's my moment expression. Can I check it? Do we know the moment someplace? If you look back to the original problem, I've got a pin connection and a roller connection. What's the moment at those? 0. So that means that I should be able to find that the moment when x is equal to 0 should be 0. Does my equation give me that? It does. You plug in x equals 0, you do get 0. Also over here at b, so the moment at x equal 18 should also be 0. Is that true? I'll have to rely on you guys to plug it in there and tell me. So somebody out there go for it. Or actually, many bodies go out and do it, and that way we can verify it.
True.
What's that?
It's true.
It's true. We have one true. Rain Man calculation. I have a feeling it's true too, but I just want you guys to verify it. Siri, is the moment at 18 equal to 0? Yes, excellent. You didn't use the right voice, but I'll give it to you.
Alexa. Alexa has different voice.
Oh, yeah. I don't have any of those. I have children. I just yell at them, they do what I tell them, right? That's the way it works? No, not. You wish. Parents will understand that. We've all been children, so we know it's not true. Okay, so let's sum forces in the y direction. And we should be able to determine what our shear force is. So I'm going to assume up is positive. So I've got shear down, negative, F2 down, negative, F1 down, negative, 15 kips up, positive. So I'm going to start with minus shear, minus F1, which is x, minus F2, which is x squared over 18, plus 15. And that would all have units of kips. So when you solve for shear, you can see it's a function of x2. What do I get? I'll put them in higher order first. So I got x squared over 18 minus x plus 15. And that should also be in kips. Do I know the shear anywhere? Well, remember, we did solve for it here, right?
Yeah.
What kind of shear force is that? Positive or negative? That's positive. So I know that the shear at x equals 0 should be 15 kips. And if you can see that when you plug in x equals 0, you do get 15. If I knew the shear at B, which I didn't calculate, but I could, this function should give you that also. What do you think the shear at B is? Remember, the total force acting down on the structure was 18 plus 18. That's 36. We solve for A being 15. What does that leave us? 21. So let's check and see if at x equal 18, is it... Oh, by the way, would it be... would the force act up or down as a reaction? Up. So what kind of shear is that? Negative. So let's see if the shear is minus 21 at the free end. Plug in x equal 18. Well, one of those 18 cancels, so you just get negative 18 minus 18 plus 15. What do you know? You get negative 21. So that's good. I like that. You may or may not have to do that one. And then, of course, our last one that we've been working on, that we haven't shown mathematically to be true, but it seems to be working, is that the derivative of the moment should be equal to the shear. So go back and take the derivative of your moment equation, and what do you get? I think it's true. So that works too. We've got a lot of things that checked off. Now, a lot of students ask me, hey, I get the moment equation. Can I just take the derivative and give you the shear equation? Yes. What's wrong? What happens if your moment equation is wrong? You just missed the shear equation. Of these two things, which is the easier to do, summing moments or summing forces? Summing forces. So I would, if I were you, I would sum the forces and make sure that the shear equation that you get from statics is related to the moment through the... That kind of backs it up. If it's not, then something went wrong. At least you get some feedback. If you just plow through and get the moment and then just take the derivative and get the shear, you could have just missed the whole thing and not had any feedback. So I had loophole kind of looking students who said, well, I'll just do the shear and I'll integrate it to get the moment. That's great, except when you integrate, you generate an integration constant. And how do you evaluate that constant? You'd have to know the moment somewhere. So you have to... I still think this is probably the simplest way to go. So, there you go. So any questions about that? That was a long problem. That was about 22 minutes. I think given your own time on the exam, you probably could have pulled it off.